Hey guys, what's going on? So today we are going to be talking about Feynman diagrams for gauge interactions. This is going to be the last use of Feynman diagrams before we get into the last section, which is quantum field theory that you can actually be proud of. That's actually a section in this book. It's the very last section in this book. It's titled Quantum Field Theory that you can be proud of. And in that section, we'll be going over renormalization groups, we'll be going over path integrals, and we'll be going over some very, very interesting things that are sort of different than what we've covered before. But in this is sort of the last topic in this chapter on Feynman diagrams. And so let's get right into it. Before we get into it, though, make sure to hit that like and subscribe button. Now let's get into it. Right, so we are going over Feynman diagrams for gauge interactions today, and what we want to do is remind ourselves of a few things. So this first video is going to be just a quick reminder, setting up the problem, and then in the next video, we're actually going to continue with the problem and finish it there. So this is going to be two videos like we did for Yukawa interactions, we're doing now for gauge interactions. So we recall the Lagrangian. So this is our Lagrangian. So we have our spinors now. We're dealing with spinors. And we have our massless gauge field, right? Our massless vector field, essentially. And then we have an interaction between our spinors, right? So between our spinors and our vectors. And this is what the gauge interaction looks like, right? So our Hamiltonian looks like this, right? It's just the integral of our interaction piece, okay? And so let's get into this, right? So this type of phenomenon, there's a very common type of phenomenon called Bhabha scattering. And the Bhabha scattering is an essential tool, if you will, or not a tool, but it's a type of elementary model that we use, or that physicists use to describe the interaction between positrons and electrons. And this is what the Feynman diagram looks for like this, right? So this is a little bit complicated, but we'll break this down. So we have two incoming particles. One is an electron, the other one's a positron. They, at some point in space-time, they exchange a particle. We can call this a photon. And outgoing, we have an electron and a positron. All right, so we can assign things to these guys, right? So we're calling them spinors. So to do this sort of thing, an electron is going to be called U. Positron is going to be called V. Okay, we've used these variables before to describe our spinors. And then we have then we have our momentum, K1, K2. So K1, K2. We have our spin labels, spin. Okay, and then as we evolve in time, I'll put time axis as we evolve in time. We then have this new spinor with a potentially different spin, R. Whereas this spinor again is our electron, and then we have this other outcoming positron, V, and a different potential spin state, right? So it could be up or down. So remember that S and R are the spins, right? So if S is 1, then we can call that spin down. If S is 2, then we'll call that spin up. But this is essentially the setup. Then we have our vertices, right? Our vertices, according to our Feynman rules, are going to be, we add, instead of an IG, we add an I, E, and a gamma matrix. Where E, again, is not, this is kind of a misnomer. E is not an electron, right? It's not an electron. It's our coupling constant. So this already is looking a little bit kind of bad notation. but we'll pursue this nevertheless. All right, so what does our scattering look like in this case? So our scattering is going to look like this. So we have electron-positron evolve into an electron and a positron, and we can put everything in our integral now. All right, so according to our Feynman rules, we have our initial state, right? So this guy is right here, and then we have our vertex, and then our other initial state, right? That's right here. And then we have our particles, actually. So I skipped this particle, but this is our K2 particle and our K1 particle. Right, so K2 and K1. Okay. And then, okay, so that is our, so that covers at least one of our vertices, okay? We can order this however we want. This is just how the book orders it, because everything's being multiplied by each other. Here's our propagator, okay? Here's our one of our final spinners. Here's our other final spinner. And here's the momentum piece of our spinner. So we've now deconstructed this guy, right? So you can see how we've gotten this from our diagram, right? So this is our Feynman diagram, and this translates to our integral right here. Okay, now this is where we're going to stop because we want to explain a few things. So we bunch all of our x1 exponentials together and all of our x2 exponentials together. Then we have this AI term and this BJ term. We're going to explain these two guys in this video. But before I do that, here's just our propagator. Okay. So that is that. So that is where we're stopping with this integral for right now, because now we want to explain these AI and BJs. So let's come down to this diagram here. Positron needs to have a spin to it. Electron also has a spin to it. Our outgoing electron has a spin, and our outgoing positron has a spin. Our BJs, let's start with our AIs. Our AIs are going to bookkeep the spin of everything coming in, and our BJs are going to bookkeep all the spins that are coming out of the black box. So here's our VS, here's our US, our two spinners, and sandwiched between them is this gamma. This is the Dirac matrix, or one of the Dirac matrices. And this Dirac matrix is labeled right here, these two guys. Same thing here, right? So nothing too drastic of a change between AI and BJ. In the non-relativistic limit, these spinners will look something like this, right? So this is in the relativistic framework, right? We've established these guys already. And when K2, so when the momentum is much smaller than the mass, our numerators here are going to be really small, and our denominators are going to get pretty big because our mass is very big. So that essentially means this guy goes to 0, and these guys will also go to 0. This guy here, again, is going to be very close to our mass, because omega is the time component of our form momentum. So that's going to be very close to our mass. If all the spatial components are really small, we're saying that the momentum is very small, then the temporal component is going to be really big. Right? So, and we've talked about that before also. So we get this, which reduces down to this guy. Same thing for our spin up positron. Right, so our spin up positron, same thing happens here and same thing happens here, so we're going to get a spinner in our non-relativistic limit that looks like this. All right. We haven't talked about, so we briefly touched about these guys. Now let's apply them. We're going to take A3, for example. We can do this with A1, we can do this with A2. And so what we do, so this dagger, again, or not dagger, but here I'll zoom in. This bar can get converted into a dagger if we apply our gamma 0. Right, this is why. Right, so our complex conjugate is equal to this guy right here, and then this 3. You can so this is a little bit weird. So we're using the mass basis gammas. You can use the other gammas if you want, but the book uses the mass basis gammas. But anyways, this is what our matrix multiplication looks like now. Right, because we've said this guy is here, this is our other incoming spin. What I'll do actually is I'll label these guys. So these are the incoming spins. Right, so these guys are the incoming spins on the Feynman diagram. All right. And when you do all this, right, you're going to get 1, right, because the first, well, you can go ahead and do this matrix multiplication. I'm assuming you guys know how to do that. We get 1. So A3 is 1. And what we're going to find out is that A2 is 0 and A1 is 0. You can do this yourself, right? This isn't, matrix multiplication should be something that you should be able to know how to do. If not, then you can go on to other sources on YouTube to take a look at how this matrix multiplication works, but this is what this looks like. So we treated both particles as spin up in this case, right? We said spin up positron and a spin up electron. So both particles are spin up, which gave us this vector. If both particles were spin down, then our AI is going to look different because these two guys are going to be different. And if one is spin up, the other is spin down, then it will also look different. So these guys are going to change again. Right, so depending on which one spin up and which one spin down, this guy is going to bookkeep. So this guy's essentially a vector. This guy is a vector that changes when this, depending on the spin of the incoming particles. And BJ is also a vector that depends on the spins of the outcoming particles. So AI and BJ are essentially bookkeeping tools to help us keep track of the spins that come in and leave our Feynman diagrams, the spins in our initial and our final states. So that's exactly what I said here. So AIBJ are bookkeeping tools for the spin of initial and final states. Right, so we have initial states here. If I zoom in, we zoom in here. So in the case that these two might be spin down, we get something like this. And this is actually, I don't want to, what I'm going to do actually is I'm going to erase these guys. Don't want to mislead you on anything. But this is sort of the picture we want to keep in mind when we are considering, what these AIs and BJs are. Right, so the spins are what we're bookkeeping here. Oops. So let's do this. So what I want to do actually is remind ourselves. Let's remind ourselves exactly what these spinners look like. So we saw the spin up electron look like this, spin down look like this, or spin up positron look like this. Spin down electron look like this guy. and the spin up positron looked like this guy. And this should be a 2, right? Okay. Let's do another example. It's always good to do examples. So, suppose we had spin up and spin down this time. So our spin up, we had one spin up here already, right? So our spin up, this guy, is right here. This is our positron. So we could do, before we actually do this, right? The positron, guys, the 1 is either going to be in these 2 slots. For the electron, the 1 is either going to be in either these 2 slots. So electron slots, positron slots. All right. Same thing. We can bookkeep these guys here, but I'm just going to do these guys. So again, this is just an example. So let's calculate A3 again. We can calculate A2 or A1 if you want to, but I'm just going to calculate A3. And look, I'm calculating A2 over here. So calculating A3, this is it, right? So these are our 2 guys right here. This is our gamma 3 and our gamma 0. We get this guy here, right? Because this first row, it matches the configuration of this column. So we get this guy. And then we get this guy is going to remain the same because the first row here corresponds with the same configuration of the column. Everything else is going to go to 0. So we have these 2 guys and this goes to 0. That's kind of interesting, right? Because A3, for the case where this was spin up, this actually was 1. So we can see how these guys are different. Let's calculate A2. Right, so A2, this is our gamma 2. Again, this is all on the mass basis. In the mass basis. So A2, so this guy here, our second row, corresponds to the configuration here. So we're going to get our I here. And then we get this guy here corresponds to this configuration. So I times 1 essentially is going to give us I. Right, so our A3 and A2 look like 0 and I respectively. All right, and those are all the examples I'm going to do. All right, so you can do more examples like this, but this is really all this is just a bunch of matrix multiplication to bookkeep what our spins are, the state of our spins. Let's touch upon one last thing here before we call it. And this is the relationship between these bookkeeping tools and our four momentum, because this is going to be important for evaluating our second order approximation to our Bhabha scattering. So we have this AI here. This is our bookkeeping tool that accounts for the spin. We have a four momentum. We call it the spin is dimensionless. So the spin is just 1 or I. And so if the spin is dimensionless, then our four momentum is going to be here. Dimensionless times something four momentum. Well, that's just going to give us a four momentum. Okay, so this is going to be important to know. And here also, incoming spin, and an outgoing spin, well, you can show for yourself that this relationship also holds, right? And this is going to be important because what we're going to do in the next video is we're going to put these guys into our completeness relationship, right? Because the completeness relationship shows up in the propagator. And so, again, these are just things to keep in mind for our next video. So if you like this kind of stuff, make sure to hit that like and subscribe button, and I'll see you guys in the next one.